Hello, welcome to the course Electronic System Design. Today we will discuss about the basic steps which we take to design a complete electronic system right from the scratch. So we have various stages where we can work on. For example, we can start from the device design all the way to the circuit design, gate design and the complete electronic system design. So in today's lecture, which is an introduction lecture, we will discuss about all these steps which we take in brief, and then later on in the course we will discuss them in the detail. So let's start from the today's introduction class. So we have electronic design stages. In these design stages, we start from the very basic step, which is a device design. From this device design, we go to the next step, which is called circuit design. From this circuit design step, we go to the third design stage, which is the gate design. After gate design, we have something called module design. After module design, we complete the IC design or the integrated circuit design. And once we complete the IC design stage, we design the complete system, or we can say the system design. So these are the 6 design stages which are very typical to any electronic industry or any system design application. We start from the very basic, which is the device design stage, where we take the silicon and we make a device which is something called a MOSFET or a BJT. This is the device design stage which is done at the very first. From these devices, we develop some circuits, for example, inverter, AND gate, NOR gate, NAND gates, and different types of amplifiers. That is the circuit design stage, which is using these devices developed by the first step. This circuit design stage develop something called a library where we make all the circuits and keep in a something called box or something, which is called a library design. From this circuit design, we come to the gate design, where we develop some digital gates using these circuits. From these gate design, we develop some modules, the bigger modules, for example, ALU, arithmetic and logical unit. That ALU design is using all these gate design, which is a digital design module. From these modules, we put several modules together to make a complete IC, which is the IC design or integrated circuit design. This is the stage where we club all these designs, all these modules, whatever we have developed, we put them together on a silicon and fabricate it using standard CMOS technologies. Once this is fabricated, we cut them using laser cutter or something. Then we make a discrete ICs or IC components. These ICs, then we take multiple of these ICs, one IC, one particular function. So we take multiple of ICs to perform multiple functions, put them together to make a complete electronic system, which is a system design stage. So these are all 6 design stages in a electronic system design. So let's discuss each one of them in brief. So let's start first with the device design stage. So in device design, so in the device design stage, we develop something called a MOSFET, which is a metal oxide semiconductor field effect transistor. This is a basic switch we fabricate using the CMOS technology. So let's draw the MOSFET structure. We start with a P-type substrate. On this, we have a gate oxide. This is SiO2 or the silicon oxide. This epsilon is typically 3.9 epsilon naught. And we have source and the drain. This is typically N plus, and this is N plus. And then we have, on top of gate, we have connection, typically polysilicon, or it can be a metal as well. So in 3D, the MOSFET structure looks something like this. We have this distance as the length of the channel, and this is the width of the channel. This is also N plus. So this is a typical structure of a MOSFET. MOSFET is a basic switch which we fabricate on silicon. This MOSFET is a field effect transistor. It means we apply the voltage at the gate to produce a field, electric field in the channel, and this electric field generates charge carriers, and hence the device conducts. So MOSFET is called, why? Because we have three different structure. One is metal, oxide, semiconductor. So we have the gate. On the top of gate we have a metallic connection which is M. Then we have this silicon oxide gate which is SiO2. So O comes from this region, and below this we have a p-type substrate which is typically a silicon or a semiconductor. So we call it MOS, the metal oxide semiconductor, and this is a field effect transistor which acts on the application of voltage at the gate. We have two more terminals to this, which is, one is source, the second one is drain. The source supplies the current to the device, and this current or the charge carriers, they flow from the source to the drain below the gate oxide, and they reaches the drain. Drain is the collector terminal where where the current is collected. So we have source, gate, and the drain. So this terminal, or this we can say, this is the source terminal. This terminal is the gate terminal, and this terminal is the drain terminal. So this structure is typically fabricated by various processing steps. For example, we use multiple implant and lithographic steps. So this is the structure which is fabricated using multiple implant or lithography steps. We start with the silicon and we do multiple implants to make source and the drain regions. We do multiple lithography steps to pattern the gate over this structure, and gate is the very crucial component of this device and which is very difficult to fabricate, because the silicon oxide layer which we are growing on this oxide, this should be of very high quality so that the performance of device is very good. So now we will discuss how this device actually works when we apply the voltage on source, gate and the drain. So MOSFET working. And we are considering an enhancement mode MOSFET. So we'll discuss the cross section of this MOSFET. We have this gate and then we have source and the drain region. This is source, which is N type, or we can say the negative type, and below we have substrate, which is P type, which is having excess of holes. So we have plus all over the body. When we start, we apply the source as 0 volt. P type body is typically at the 0 volt, always grounded. Drain also we are keeping at 0 volt only, and now we are applying, initially the gate voltage is also 0. So when gate is at 0 volt, it means the P body is having excess of holes and there is no current flowing from the source to the drain, because there is no channel formed below the gate, or there is no charge inversion below the gate oxide. This is the case 1 when we are not applying any voltage on the device. In the second step, now we apply a voltage at the gate so that we can create a electric field under the gate oxide. So this is first stage. In the second stage, we apply voltage at the gate source and drain are still at 0 volt, and gate is now having a voltage applied. So what happens when we apply a positive voltage on the gate? This positive voltage will create an electric field below the gate oxide, and this will push away the holes which is positively charged away from this surface, away from the gate oxide surface. So this positive charge will be pushed away from the surface, and the negative charge, which is the electrons present in the p-type body, those electrons will be accumulated under the gate oxide, and these electrons will form something called the channel in the device. So we have positive holes all over the body, but below the gate oxide we will have negative charges which have accumulated because of the positive voltage applied at the gate. So these negatively charged carriers, these are free to move because they can move in any direction. Now if we see this device, we have a conductive path from the source to the drain. Drain is also a negatively n-type region. So now we have from source to the drain, we have a complete path where a current can flow from source to the drain using this channel. So this is the case B when we have applied the voltage only at the gate. So applying the voltage at gate is just creating the channel below the gate oxide. Now in the third step, we will apply the voltage at the drain also, so that we can have a constant current from source to the drain. Right now source and drain both are at same potential, which is 0, so there is no current flowing from source to the drain. So let's see what will happen if we apply the voltage at the drain. The source is still at 0 volt, gate is applied a positive voltage, and now the drain is also applied a positive voltage with respect to source. Now these electrons which are present in the channel, they will see a positive voltage to the right, so they will move towards the drain. If we apply a higher voltage at the drain, it means the electric field towards the drain is high, which will pull more electrons from the channel. So earlier, which the channel earlier, which was the horizontal or rectangular channel, now that channel will not no longer will remain a rectangular channel, but it will become a triangular one, because towards the drain end there is a high electric field which is pulling away all the electrons from the channel. So the thickness of channel towards the drain is smaller compared to the thickness at the source. So we will have the channel something like this, the rectangular in the C case. However, in the case B, the channel is perfectly rectangular. So we can see at this point there is a high electric field which is because of the voltage applied at the drain. So channel is no longer a rectangular channel, and this gives rise to something called the channel length modulation. So this is how this device works. First we apply the voltage at the gate to produce the channel under the gate, and then we apply a voltage at the drain which is positive compared to the source. So this channel participates in the current conduction from source to the drain. Then amount of current depends upon how many charge carriers are there in the channel. If we have more carriers in the channel, then we have a higher current. If we have less number of charge carriers in the channel, it means we have a lesser current. And the amount of charges or the number of charge carriers in the channel, that depends on the gate, how much gate voltage we apply. So the gate voltage dictates how much charges we have, and the voltage at the drain is used to carry away the charges or to conduct the current from source to the drain. So in the next step now, we see a MOSFET equation. MOSFET characteristics and equations. So if we apply a drain voltage at this MOSFET, which we saw in the last slide, and we measure the drain current at the y-axis. So y-axis is the drain current and the x-axis is the voltage between drain to source. Then a typical characteristic for a MOSFET look like something like this. This is the point VGS minus VT. VT is the threshold voltage of a transistor, and then we have a saturation current. The value of this saturation current comes out to be half mu n C ox W upon L VGS minus VT whole square. So this is the value of the saturation current. So as we can see from this graph, when we apply a small drain voltage at the MOSFET, then the current rises linearly with the voltage. It means the device is following Ohm's law. When we increase the voltage, the proportional increase there is there in the current. So this region is called the ohmic region, where the current is following Ohm's law. But as we keep on increasing the voltage, at some point there is no enough charge carriers in the channel which we can pull away by applying high voltage. So even if we apply the high voltage, there is no charge carrier, so current will not increase. So the current is going to saturate at some point, even if we are applying the higher and higher drain voltage. So that we can see here by this flat region, we are increasing the drain voltage, but the current is not increasing because there is no charge carriers in the channel. This value of current is called the saturation current, and the equation for saturation current is half mu n C ox W by L W upon L VGS minus VT whole square. These are standard terms used in this equation. Mu n is the mobility of charge carriers, typically electrons. C ox is the gate oxide capacitance. W is the width of the device. L is the length of the channel, in fact. VGS is the gate voltage that we apply with respect to the source, minus VT, the threshold voltage of the MOSFET. So this is a typical equation for saturation current. However, if we see in the last slide, when we apply the drain voltage, the channel is no longer a rectangular channel. The channel kind of having a very small thickness towards the drain, which is called channel length modulation. That happens if we apply the higher drain voltage. So in this graph, we are assuming that channel length modulation is not happening in the device. However, if we consider the actual case where channel length modulation will occur, then this graph looks something like this. So instead of saturating at a constant current, the current is actually increasing. So this is the case without channel length modulation, and this is the case with channel length modulation. So the current equation, if we consider the channel length modulation, the equation for the current drain current is half mu n, the oxide, W upon L, VGS minus VT whole square. So this is the value of current without channel length modulation, and one more factor also included in this to consider the effect of channel length modulation, which is 1 plus lambda VDS. This lambda considers the effect of channel length modulation, and if we see this equation, if the drain voltage is increasing VDS, it means the whole value of current will increase. So these are the two graphs, one with channel length modulation, one is without channel length modulation. Next we will discuss the device modeling. Once we make these devices, generally we make a model. Model is something, the representation of device characteristics using some equations which we can use a computer to solve some designing of these devices. So we have these characteristics which are generally measured on silicon once we fabricate the device. Once we have these characteristics like ID versus VDS, ID versus VGS, and for different values of VDS and VGS, we take these values and try to make equations for these graphs so that we can use a computer to solve these equations. So we make something called device model, and the first device model which is primarily used everywhere by industry and academia, that is called a BSIM model. The full form of this is Berkeley short channel IGFET model. So here if we see, this is B, this is S, this is I, and this is N. So this is Berkeley short channel IGFET model, which is nothing but the set of parameters which we use to mimic the device using equations. For example, a BSIM model has lot of parameters. For example, TOX, which is the oxide thickness. We can have L, which is the device length, W, which is the device width, and so on. We can have like lambda, which is channel length modulation factor. So BSIM model is nothing but the collection of all those parameters which are used to mimic the device using the equations. So BSIM has the transistor is modeled using multiple device parameters. Some of them parameters are something like L, which is the channel length, W, the channel width, VT, which is the threshold voltage, lambda, for example, the channel length modulation factor, and so on. So this BSIM, which is a model, this is primarily developed by University of California at Berkeley. So that's why the name is called the BSIM Berkeley short channel IGFET model. And this is a nothing but a set of parameters which we are using for modeling the device. And these parameters are the physical parameters which are linked to the actual device structure which we are making on silicon. For example, L is the channel length. So how much channel length we have fabricated on silicon, that measured value we can put as a value of L. W, for example, the channel width, how much we have fabricated on silicon, that is the value of W. VT is the threshold voltage which we generally measure using electrical measurements, and we take those measured values and put as a VT. Lambda is also measured something like electrically only. So this BSIM is nothing but the set of parameters which are provided generally by the foundries who are making these MOSFET devices. So these foundries, we call it, who make these devices, these foundries make the MOSFET on silicon. They measure the electrical parameters and geometrical parameters and put them together in a set of equations, something called the model for the device. We take these models and we can use some CAD tools, which are computer aided design tools, for example Cadence and Synopsys. We take these models and now we can represent the actual device using these equations or these models, and now we can start connecting more than one devices together. In fact, we can use hundreds of devices which are using hundreds of models. We can start connecting them together and we can make a complete circuit using these devices. So these models, BSIM models, these are primarily developed for a MOSFET. So, however, we are using them for other type of device as well, but they are primarily developed for MOSFET, and these are physics based models. So, what's the advantage of a physics based model is this model is scalable. When we started like 40-50 years back, the MOSFET dimensions were very large, and now we are every second year we are kind of reducing it by half. So over the time, the device structure of a MOSFET has shrunk drastically. However, these models which are developed by that time, they are still valid for today's MOSFET with some advancement. That is happened because these models which is BSIM, this is a physics based model considering the physical parameters of devices and the physical parameters like physics based parameters. So those are taken into developing this model. So this model is scalable. We can apply to advanced nodes as well. There are so many parameters now over the time we have added in this BSIM model. Typically, just to model a single threshold voltage, we are using nowadays more than 25 parameters just to model a threshold voltage, because over the time the complexity of the device has increased so much. Another point is these BSIM models, these are small signal parameters. Small signal means the voltage, the signal we apply on the circuit, that we are considering typically is a small signal compared to the supply voltage we have. These models are not very well applicable for large signal circuits such as power amplifiers or so, but most of the time these models are good enough to represent most of the circuits. Only in very special cases where we use large signal applications, that time we have to go to some other type of models. Otherwise, most of the time we work only with BSIM, which is a small signal models. So we have few points here, which is this is primarily developed for MOSFET, these are physics based model, and scalable. There are more than 25 parameters. Just to model VT. VT of MOSFET. And we have small signal applications. So once we have the device fabricated, we develop the equations and then we develop the device model, and these models now we can use in the next stage, which is a circuit design stage, to develop complex circuits using these devices. So the next stage we have is circuit design stage. Second step or the second stage is circuit design stage. In this design stage, we take the models developed by the foundries and we include that in a program which is something called a SPICE simulator, which we use for simulating these structures. We make something called a net list, which is nothing but the connections we specify for all these devices, and we specify the type of analysis we want to perform. So that code is called a net list. In that net list, we include these models, which are BSIM models, and we simulate this net list using a software which is called SPICE software or the SPICE simulator. So we make something called net list. In this net list, we have electrical connections. We specify the electrical connections. We specify the type of analysis we want to perform, and we also include models. So this is the model which is coming from the first stage of device design, and using these models we are creating a net list. Now this net list we simulate using SPICE simulator. This net list goes to a simulator called SPICE, which can solve these equations and prepare the electrical voltage and current at the node. So SPICE simulator is nothing but an algorithm which solves all Kirchhoff's law and continuity equations using these models and find out all the node voltages in that mesh or in that circuit whatever we make. All the individual voltages are captured by SPICE simulator, and these voltages we can analyze using some software or GUI provided by SPICE. So we make in netlist we make circuits which is nothing but multiple devices connected together. In this case we are taking just a PMOS and an NMOS, connecting them together to make a inverter. So this is a PMOS and this is an NMOS. This is supply voltage VDD, this is ground GND, this is input and this is output. So in net list we will take two models, one for the PMOS and one for the NMOS, and this model will have three terminals, for example source, gate and the drain. For PMOS, the drain is connected to the drain of NMOS and that terminal is called, we are calling it as a output. Gate of PMOS is connected to gate of NMOS and we are calling it as a input of inverter, and source for a PMOS is connected to the VDD, and source for a NMOS connected to the GND or the ground. So this is how we make a netlist. Now we specify what type of analysis we want to perform. For example, here in this case we want to perform a DC sweep. We want to sweep the input voltage from very low value to a very high value, and we want to analyze how the output is going to change. So this is an inverter. When we apply a 0 volt at the input, output is high, and when we apply high at the input, the output is low. So now we see what SPICE is going to provide us. This is V in and this is V out, and here we are sweeping V input from 0 to high value such as VDD, and V output we want to see. So initially for a low value of V input, the output will be high, and as we keep on increasing, the output is going to decrease, and at some point this will become 0. So this is the typical characteristic of a inverter: output high for input low and in output low for input high. We do multiple iterations of this circuit design. For example, we have multiple parameters which we can play around for PMOS and NMOS to get the desired characteristic. So this output versus input voltage is the characteristic of circuits. We want to make a circuit for particular application, so we have some specifications in our mind. For example, the slope of this curve should be something like this as per the specification. So we can do multiple iterations in SPICE simulators to achieve the desired output waveform, this output versus input, or it can be the transient waveforms. This is the DC simulation. So once we achieve the specifications which we want from a circuit, then the next step for the circuit design is the layout design, which we are clubbing here in the circuit design itself. So once we make this circuit and we are happy with the performance, then we make something called a layout, and layout is nothing but the geometrical representation of the device. So we can roughly draw a layout for an inverter. So this is the VDD rail, the metal, and then on the top we have a PMOS, these are contacts, and then we have a polysilicon which is the gate, and this side we have the output. This is the ground rail. this this section is NMOS and this section is PMOS. This is the gate. This is the output terminal. This is the input terminal, and this is the supply, and this is the ground. So this is typically a graphical representation of the device which we fabricate using the circuits which we developed using SPICE netlist. So these circuits are generally designed by circuit designers who prepare all these circuits. They are different kind of circuits. This is just an example of an inverter. There may be the memory circuits, SRAM cells, and so many other circuits. Designers make these circuits and put in a space something called a library of cells, and we have so many libraries. For example, we have a core cell library, we can have a IO cell library, we can have a memory cell library, and so many other libraries, analog libraries for example. So these libraries are developed using these models provided by the foundry, and circuit designers use SPICE simulator to make circuits, and if the performance is met, then circuit designers make layout of that circuit, put it in the library. The next stage is the gate level design. In the gate level design, we make the gates, the standard digital gates using these devices or these circuits. For example, a NAND gate or a NOR gate. The NAND gate is a universal gate which we can use to implement any digital logic. So we can develop these gates using these circuits which we developed in the previous stage. However, in this stage, we want to transit from the SPICE simulator to the something different, which is called a hardware description language or the HDLs. Why do we want to switch from SPICE to a HDL? Because the SPICE, if we can remember, SPICE uses models developed by the foundry, and one model represent one device. If we use multiple devices in a single circuit, for example 10 device, we use 10 MOSFETs in a circuit, then we have to solve the model 10 times, once for each and every device, which is very computationally intensive. This model is not very small. Over the time this model has become complex, so it's very difficult to simulate a circuit having more than 100 transistors using SPICE simulator. However, results will be very accurate, but the time complexity is very high. So at this point we want to switch from SPICE to HDLs, where in HDL, the hardware description languages, we just represent the logic by 0 and 1. We are not very much interested, or we are not very much concerned how the transition is happening from 0 to 1. So we are representing the output only by 0 and 1s, and we want to solve so many circuits together to get the desired output. So HDLs can do that work. So now we have digital design stage. where we prepare the digital model using Verilog or VHDL. These are the two primary languages used for digital design. So in this case, for example, we have a NAND gate here. So here we have something called a NAND gate, which we have two PMOS on the top connected in parallel and two NMOSes connected in series on the bottom, and one PMOS and one NMOS connected together to form a input A, and the other PMOS and other NMOS are connected together to form the input B. So it is a two input NAND gate, and the output is produced at the junction of PMOS and NMOS here. So this is a gate which is a NAND gate, and this we can use to implement any kind of digital function. Now when we make this as a gate using digital design, we are not concerned about how the output is changing when the input A and B are changing. We are not interested in the transitioning the sharp curves which output follows from high to low. We are interested only when the input A and input B are changed and they are stable, 0 and 1 whatever. Then what is the out stage of the output, whether it is 0 or it is a 1. We are not interested in the transition. So this reduces the complexity very much, because handling 0 and 1 is very easy for a computer language. Now we use Verilog or VHDL to implement this NAND gate, and we can see an example of NAND gate using Verilog. So Verilog code for a NAND gate. So we can instantiate by writing module logic gate, which has three terminals. One is C, A and B. C is the output, A and B are the inputs. So we need to define that. So output C semicolon, input A comma B semicolon. Then we can define a NAND function using function NAND N1, which is an instance name, C comma A comma B. and module. So this is a small code for representing a NAND gate, where we start using the term module, logic gate C, A and B, where we define all the input and output ports for a module. This NAND gate has 3 terminals, 2 inputs and 1 output, and output we are calling it C. So we have to define that using output command, output C, and the input is A and B. Then we define the relation between input and the output. So that is defined using the expression NAND, and NAND is a term which is telling Verilog that there is a NAND functionality between input and output. N1 is the instance name of that particular instance, CAB, where C will perform as per A and B and according to the NAND functionality. And module is to complete the module ends here. So this is a typical Verilog code. We can write multiple Verilog code for different types of gates, and these are very easy to simulate using Verilog language. So this is the third level where we design the gates using Verilog and VHDL in digital domain. We switch to digital domain because we want to have so many devices using these MOSFETs we want to fabricate, but the spice is very time consuming and very computationally expensive. So we switch to the Verilog or VHDL languages, which can easily solve multiple circuits together. However, the spice simulation is very close to silicon, and in digital design we are concerned only about the input and output. We are not very much interested in how the output is changing or the transitions in the output. So this is all for today. In the next lecture we will continue from the fourth module, which is the module level design. Thank you.